Hello everyone and welcome to MV Tutors. I'm Tulu and I'll be looking at measuring the rates of reactions. Okay, so before we continue, please do not forget to like our videos and also subscribe to our channel. Also, please spread the word with those who will be doing matric in 2022 or even upgrading. Alright, otherwise, if you want to book a session with us, go to www.mvtutors.co.za. Alright, so how do we measure the rate of a reaction? Okay, so one way you could either study the rate at which the products are being formed or they appear, okay, or you could study the rate at which reactants are used up, okay, while the reaction occurs. All right, so experimentally, there are quite a few ways in which you can do that. First of all, we could actually measure the turbidity. Okay, so basically, that's when you have your reactants, and while the reaction is happening, there's some cloudiness, basically, where your precipitate is busy forming. And once it's very cloudy or milky, or basically it's not so clear anymore, well, that's when the reaction has basically finished or completed. So you would measure the rate. Obviously, when we say rate, think about time. So in these experiments, we will have a stopwatch, okay, just to measure at what rate all of this is happening. All right. You could also measure the gas volumes produced. So in some reactions, there's a gas that forms, okay? So in that case, you would measure that gas. That gas would either go through a gas syringe, okay? So in that case, then you would be able to measure the gas that is formed and also take the time in which it forms. Okay, and then it gets to a point where there's no more gas that is forming, so the reaction would be done at that point in time. And sometimes you actually look at the color. If a reaction changes color, and then it's a constant color throughout after the reaction occurs, then you know, okay, fine, something has happened, a color has changed, so my reaction is complete. And lastly, we would look at the change of the mass of the reaction, especially if a gas has escaped. Okay, so in your reaction vessel, you would have your reactants, and while the reaction is going, there'll be some gas. So instead of having a gas syringe there, you let the gas escape, and then you measure before everything happened, and then you measure after the gas has escaped. Then you can see, okay, fine, the mass there has reduced. Okay, so now we're gonna actually look at it with sketches that I tried to draw. Alright, so with experimental technique 1, we are actually gonna measure turbidity. So what you would need is white paper. Whether you cut it out in a circle or you leave it as a rectangle, it doesn't matter. But I guess if your flask is round, you would want to put it in a circle. And then in the middle of that circle, on your white paper, you draw a black cross. Okay, then you would put in your reactant. So in this case, we have sodium thiosulfate or thiosulfate. This is how you write it. Okay, my pen has disappeared. There we go. So this is sodium thiosulfate. Okay, so this sodium thiosulfate or thiosulfate, you add it with diluted hydrochloric acid. Okay, diluted hydrochloric acid. And then your products, well, you're gonna get sodium chloride, so that would be a salt that is dissolved. You get water, okay, and then you get what is it, sodium dioxide, sulfur dioxide. Did I say sodium? Sorry, sulfur dioxide. And then you get the precipitate, which is sulfur, and that precipitate that actually forms is yellow. Hence I tried to put a yellow solution there. Okay, so basically you have your flask, you're gonna put in your reactants, and then you're gonna, like, if this was the flask, yes, you're gonna stir it just like that. And then, so over time, like I said, with turbidity, it's like there's this cloudy, reaction that happens. So once it's done, how do you know that the reaction is complete? Well, basically, you can't see that black cross anymore. Okay, so you would actually take your stopwatch and then measure in intervals. Okay, in seconds, that would be preferable. You would measure over time, like the turbidity. Okay, every 5 seconds, I'm measuring until you don't see the cross anymore. Okay, so that's basically what happens when you measure turbidity. One thing with all these experiments or these techniques is that you should keep temperature constant. They like asking questions like that, like what should be kept constant during these experiments. So if you should have one variable that keeps changing and one that is constant. So temperature with these is constant. Okay. And now we get to experimental technique number 2. Basically, that's where we measure the volume of a gas product. So let's say we have magnesium in its solid form, and then we add, okay, let's look at the image. So let's say we have magnesium there, okay, as a block in its solid form, and then we keep adding hydrochloric acid, okay. I would assume it's diluted. And then at the end, we have the salt, magnesium chloride, which would have been dissolved, and you have some hydrogen gas that will escape. Okay, but as it escapes, as you see here, so you have a stopper there, which I made brown because I thought about a cork. So, yes, a stopper. So, your gas would basically go inside your delivery tube all the way, okay, and it would get into your gas syringe. So here, you, like with the gas syringe, I don't know if you've seen a syringe before, you have like a rubbery material inside which will basically move as the gas comes in. The gas is strong enough to move that rubbery thing in the syringe, okay. And while you're doing that, so basically you're gonna start your stopwatch the moment you add the reactants, okay, and quickly close with the rubber stopper. That's when you start with your stopwatch, and then you keep taking it at regular intervals. And also, yeah, I think you need a partner here, because as you are checking out your stopwatch, you need to be taking down the measurements from the gas syringe, okay, with time. So you're gonna plot a graph of volume of gas produced, okay, whatever you're gonna measure your volume in, either cubic centimeters or cubic decimeters, is really up to you. And then you're gonna take the time on the, so on your independent, or what would be your independent variable, that will basically be your time. Time is not dependent on anything, it just happens, okay. But the volume of gas produced will be on your dependent variable, which is the y-axis. Okay, so you'll have your graph there, volume of gas produced, versus your time. Okay, please don't forget to label your graph if ever you are asked to draw it. Okay, and then here I've put 1, 2, and 3, and basically you need to interpret that. What does that mean? Okay, so I'm just gonna put there, maybe we use a red color, something quite bright. So if I were to take the gradient there versus the gradient there versus here, well, basically it's flat. Okay, there isn't really a gradient. So at 1, what tells you is when you have a really steep gradient, it means that your rate of reaction is actually happening quite fast. Okay, so they initially have an increased rate of reaction. Okay, once you get to number 2, well, your reaction is sort of slowing down. Okay, remember at the beginning, you have your reactants there, and this reaction is busy happening. Your bubbles are forming, you're measuring the volume, you're taking the time. So everything is quite quickly at the beginning. And then it starts slowing down. So your reaction rate there at number 2, it's actually, it's, it's not exactly fast, it's not exactly slow, but it is slowing down. It's slowing down a great deal. And then when you get to number 3, well, basically where your graph starts becoming quite flat, that's when you know that the reaction has stopped, or it's coming to a stop, or the reaction is completed. Your products are formed. Okay, no more gas bubbles in this case. Yeah, so your action has come to a stop. And in this case, you can see that you basically have your limiting reactant, and your limiting reactant, I actually just mentioned it briefly. So pretty much when your bubbles have stopped forming, you know that, yeah, let me just put it there. So the bubbles have stopped forming. Okay, once you get to that flat portion, your bubbles have stopped. Okay, so whatever it is that assisted in hydrogen gas being formed, which is the hydrochloric acid, that would probably be your limiting reactant. Okay, so yeah, it has come to a stop. Your bubbles cannot form any longer. Your hydrogen is done. Hydrogen gas, that is. Okay, so yes, that is basically that. And then we get to experimental technique 3, okay, where we measure the total mass of reactants and the mass that is lost. Okay, so here you basically have again your flask with your reactants, okay, and we've placed their cotton wool so that it doesn't, when your gas forms or your bubbles form, they can escape, okay, but it's hindering the rate at which it can come out because the bubbles just go out completely. Then yeah, it's quite difficult to measure. All right, so you have your flask, you have your reactants, okay, your cotton wool is there, but the gas will escape through it. And then we have our electronic scale. So what you will do, you will measure everything before the reaction starts, okay? You would have measured it. Hopefully your gas doesn't escape that quickly, hence you put the cotton wool, right? So you measure it beforehand, and as you keep going, so this electronic scale will have probably where it will write what mass you have left. So you keep taking still at regular intervals, maybe 5-second intervals, all right? And then until the point where your gas stops or your bubbles stop forming, okay? So you would have seen at that point in time, this is the mass that you have, which should have been less than what you started with because your gas is escaping. So again, you're going to use your stopwatch for that, and you'll continuously measure the mass, okay, as we go on. And basically, you can present this information in 2 graphs, okay? Firstly, it could be the mass lost, okay, over time. So obviously, the mass that you lose over time will be a lot. Hence, you see it's actually going up, all right? When you started, you didn't lose any mass, okay? When you're here at the beginning. But at the end, or rather when you reach this point here, you've lost all the mass you could because the bubbles have stopped forming, and therefore you have a straight line going forward. All right, let me just remove that. And then on the other side, you can either measure the mass lost, or you could take the you can take the mass of your flask and the reactants. Okay, so obviously it will start out being a very big value, and then as your gas escapes or the bubbles form, it will reduce until you reach such a time where your bubbles maybe stop forming and now your mass is just constant with time. Okay, so again, we're just going to describe briefly what happens at 1, 2, and 3. So you can actually see for both graphs, okay, the mass loss versus time, as well as the mass of the flask and its contents versus time. Initially, okay, if you look at the gradient or the slope, it is quite steep, okay? So here you actually have a very steep slope, okay? Even here you can see the slope is quite steep. So the steeper your slope, the higher the reaction rate. Okay, I've actually said that in the previous graph. I'm just going to indicate with 2 arrows. That is really when your reaction rate is the highest. That is when your products are busy forming quite quickly. Okay, then when you get to 2, not step 2, but position number 2, if you take the slope there, you can see that it's actually quite flat compared to at position 1. So that tells you that, your reaction rate is actually slowing down. Okay, so you're not forming as much products as you did when you compare it with position 1 in both cases. So your rate of reaction is decreasing slightly, gradually decreasing. And then you get to position 3, where there you can see it's very flat. Okay, so basically the reaction has finished, or it has been completed. Okay, that's a nice way to say it. Your reaction is complete. Okay, so in the case of the sketch over here, how do you know that the reaction is complete? Well, basically your bubbles have stopped forming. Okay, in the case of technique 1, how would you know that your reaction is complete? Well, basically you can't see the X anymore, or you can't see it as clearly as you would before the reactants, or before the reaction was busy happening, occurring. Okay, so that's basically that. As long as you understand the graphs, how to interpret them, okay, especially using gradients or slopes, then you're good to go. So we're going to look at a question paper. Oh, the limiting and the excess reactant. I said I'll get to it. Guys, please don't mind. My nose is so blocked. I don't know what to do. I've tried these nasal sprays. They don't work. This is sabotage. But anyway, as long as you can hear and understand. So the limiting reactant, that's basically the reactant that is used up during the chemical reaction. So once that is used up, nothing can happen anymore. So in the case of bubbles, once the bubbles have stopped forming, that's it. You can't form anything else. That's your reaction, or rather your chemical reaction is complete. Your excess reactant, on the other hand, well, that's the reactant that is not all used up. So there's some of it remaining. Okay, that's why you would get in questions for acids and bases where they would say there was a reaction and then you have excess hydrochloric acid or excess sodium hydroxide that was used somewhere else. Okay, so basically that's that. It wasn't used up. Not all of it was used up during the chemical reaction. Okay, so we're going to look at question 5.2. Okay, from the 2016 paper. Okay, now my thing is malfunctioning. Okay, I'm just gonna set it up quickly. Okay guys, I managed. Let me just shift this a bit. Alright, cool. So graphs A and B below were obtained for the volume of oxygen produced over time under different conditions. So we get graph A, which has a gradient that is steeper than graph B. Hint, hint. You know, the higher the gradient or the slope, the higher the reaction rate. Okay, but ultimately, we can see there at time 60 seconds for graph A, the reaction was complete. Whereas graph B, at 120 seconds, we can see that the reaction was complete there because it's just flat. Alright, so on the y-axis, your dependent variable, that is the volume of oxygen gas, okay, measured in cubic decimeters. And then on the x-axis, which is time in seconds, that is your independent variable, because time just, it's independent like that. Like Destiny's Child. Okay, so basically that is measured in seconds. And then yeah, let's go ahead and answer the questions. Ooh, I do not like the red pen. That is for marking. Okay, 5.2.1. So it says calculate the average rate of the reaction in cubic decimeters per second. So they're actually giving it to you. So the reaction rate will be in terms of volume per time, right? And that volume is cubic decimeters and the time is in seconds. So between 10 seconds and 40 seconds. Okay, so we need to get the average rate. So for a time of 40 seconds, okay, we take the biggest subtracted. So now at 40 seconds for graph A, what is the volume? So 40 seconds for graph A, the volume, well, it looks like, okay, 40 seconds graph A, it looks like it is 52. Okay, so yes, it looks like it is 52 for 40. Okay, And then for 10, well, where is 10? So 10 is somewhere here. 10 gives me, I've lost my place now. Let me just sketch it. Why does this comment page come out? Okay, anyway, for 10, so we have 2, 4, 6, 8, 10. 10 is here, and it goes all the way till there. So it's 16. Okay, so we have 16 over there. Alrighty. So now we can actually calculate then. Alrighty, now I need a calculator. Okay, let me get a calculator. I am disorganized. I had it and then now I've lost it. Okay, calculator. Okay, let us do this quickly. There we go. Like things are just happening so slowly. Okay, there we are. We have the calculator. We can calculate. Okay, so we have the 52 minus 16, and then we have 40 minus 10, which is 30. So our answer is actually 1,2. Alright, so they wanted in cubic decimeters per second, so it's 1,2 cubic decimeters per second, and that is 3 marks. Alright, so 5.2.2, use the information in graph A to calculate the mass of hydrogen peroxide used in the reaction. Assume that all the hydrogen peroxide decomposed. Okay, use 24 cubic decimeters per mole as the molar volume of oxygen. So basically, okay, I didn't start this question from the beginning, so like hydrogen peroxide, what's happening? So we're just gonna get the equation. Here, so we have hydrogen peroxide, so let me just see. I can reduce the pen a bit. Okay, so we have hydrogen peroxide, which is H2O2. That's the chemical formula for hydrogen peroxide, and then there are 2 moles of it. And then 2 moles of hydrogen peroxide give us 2 moles of water. And we also get oxygen. Okay, 1 mole of oxygen. So that is the equation. So they're saying use the information in graph A to calculate the mass of hydrogen peroxide used in the reaction. Okay, so in this case, I would assume that hydrogen peroxide is the limiting reactant because once it was used up, once it was decomposed, there was nothing else. So that's where you have the horizontal line, okay? Basically where the reaction is complete. So the reaction became complete at 60 seconds. Okay, so I'm just going to note it there for myself. The reaction became complete at 60 seconds. Now, assume that all the hydrogen peroxide is decomposed. Okay, use 24 cubic decimeters per mole. So at 60 seconds, what is the volume? Oh, nice. So at 60 seconds, the volume is 60 cubic decimeters. Yes, cubic decimeters, that's it. That's the volume, okay? So at that time, that is the volume. Okay, great. Now we have been given, so if you wanted the concentration here, remember concentration is actually number of moles per volume, okay? So what I would do is I have actually been given 1 mole and I have 24 cubic decimeters. Okay, so basically that's the 24 cubic decimeters per mole they gave us. I just wrote it the other way around. And why did I do that? Well, basically I want to multiply by the volume we just determined at 60 seconds, which is 60 cubic decimeters, so that I can get a value in mole. Okay, so I would therefore say the number of moles is concentration times volume. Okay, the concentration is 1 over 24 and the volume is 60. Okay, so basically the number of moles that I have, I would then take 1 over 24 and multiply it by 60. Okay, not 0, by 60. Okay, and then I get 2 comma 5. So I have 2 comma 5, just take it up, 2 comma 5 mole of this hydrogen peroxide. Okay, so I have the mole, I'm looking for the mass. So remember, we can go to the formula sheet if you have forgotten. Remember the number of moles equal to mass over molar mass, this one over here. So I'm going to say mass is then equal to the number of moles times the molar mass. Okay, and then looking at our formula here, we have 4 hydrogen atoms. Okay, so that's going to be 4 times 1. Then we have 4 oxygen atoms, so that's going to be 4 times 16. And if you're not sure where I got those values, well, basically on your periodic table, the molar mass of hydrogen is 1 and the molar mass of oxygen is 16. So finally we know that our molar mass for hydrogen peroxide will be equal to 4 plus, what is 4 times 16? 64? Okay, so 4 times 16, yes, it's 64 plus 4, which is 68. Okay, so the molar mass is 68 grams per mole. Okay, so finally guys, we can get the grams, the mass. Wait, question 5. Okay, so we can get the mass. Oh no, my battery's low. Okay, let's finish this quickly. Okay, so yeah, we want to get the mass of hydrogen peroxide. So I said the mass is equal to the number of moles, which is 2 comma 5, and the molar mass, which is 68. Okay, so what is 2 comma 5 times 68? There we go. So now 2 comma 5 times 68, it's 170 grams. And that is our answer. Okay. Alright, the last question, 5.2.3, it is 1 mark. So let's see. How does the mass of hydrogen peroxide used to obtain graph B compared to that used to obtain graph A? Okay guys, if you look at graph A and graph A has a steeper gradient. Okay, so it means that for it to reach 60 cubic decimeters, it reached there quite quickly. Okay, for graph B, for it to reach 60 cubic decimeters, it took a rather longer time. If you want to get the rate at which the reaction occurred, you can calculate it. But if you see with graph B, it actually took 0.5 cubic decimeters per second, whereas graph A took 1 cubic decimeters per second. So the rate differs. But when it comes to the mass will be the same, because at the end of the day, you have the same amount of volume. Okay, if you look at the calculation we did before, what we really required was the volume to get this calculation going. And the volume is the same. We have 60 cubic decimeters. So if we were to say, how does the mass of hydrogen peroxide used to obtain graph B compared to that to obtain graph A? Well, basically, it is equal to. Okay, and I hope that is clear to you guys. If they spoke about the rate it took to get to that 60 cubic decimeters, then we can talk about another story. Okay, but now it's talking about the mass, and the mass is the same. Okay, so that's it for this section, and I'll see you again another time. That's goodbye from me.